Since all atoms are 99% empty space, therefore all the matter that we see is also 99% empty space, then why is everything not transparent? Yes, atoms are mostly, they seem to be empty space, right? Atoms seem to be mostly empty space. The solar system is mostly empty space, way more than 99%. And if the solar system and other star systems are mostly empty space, it means the Milky Way galaxy is mostly empty space, which means the entirety of the universe is overall, almost all of it is just empty space, right? That's the context. But coming back to the question about atoms, yeah, it's a very interesting question, very fascinating question that kind of helps us drill down into the fundamentals of physics and quantum physics. So this notion, this idea that atoms are 99% plus empty space, it's a misconception. It's a very common misconception, which originates in outdated atomic models. So you had the solar system model of the atom. There's the nucleus at the center, and the electrons are going in circles or ellipses around the nucleus, just like the planets orbit the sun. So there is one model that's the model that students usually think of when they think of an atom. And we know that the nucleus is so small and the electrons are even smaller, so it's mostly empty space. So that's an outdated atomic model. That's the first thing that's taught to students of science, which helps you visualize the atom in your mind, but it's not accurate. So in reality, atoms are not as empty as this idea suggests. And let me give you the reasons why atoms are not really empty and why objects are not transparent. So in atoms, you have electron clouds and electromagnetic fields. Atoms have a nucleus, and we kind of know that the nucleus is at the center of the atom. And these nuclei, the nucleus of the atom, it's surrounded by clouds of electrons. When you talk about the hydrogen atom, it's just one electron. But in most atoms, oxygen, iron, uranium, whatever, you have clouds of electrons. So these nuclei are surrounded by clouds of electrons that occupy a significant volume, a certain amount of volume. These clouds are not empty space. These are regions where electrons are likely to be found, and the probability of finding the electron depends on the wave function, which is quantum mechanics. I'll not discuss that. Now, these electrons are all moving around, and they generate electromagnetic fields described by the Maxwell equations. So these electromagnetic fields fill the space within and around atoms, and they interact with incoming light waves. So it's not exactly an empty space, okay, from this perspective. Now let's talk about quantum mechanics and the behavior of electrons. So in quantum mechanics, electrons don't behave like discrete particles. It's not a billiard ball, okay? They don't behave like discrete particles orbiting the nucleus. They exist in probability distributions, and these probability distributions are called orbitals. These orbitals, the effect, okay, let me show you hydrogen atom orbitals, since we are discussing orbitals. Interesting what I end up talking about. Hydrogen orbitals. Where's the screen? Let's put that on the screen. These are atomic orbitals. They are derived from the solutions of the Schrödinger equation. So this is a hydrogen wave function and so on. These are what the orbitals look like, and these do not represent empty space. These orbitals are probability distributions where you have various probabilities of finding these electrons. So there is no truly empty area in these orbitals. Okay, let's understand that now. So from that perspective, from the orbital model, from the orbital visualization, you can see there is no real empty space in these atoms. Now let's talk about the interaction of light with matter, because the question is about transparency, right? So when what is light? Light is photons. Photons are waves as well as particles. Let's talk about photons as particles for a bit. So when light, which is made of photons, it encounters matter, it interacts with the electrons in the atoms in various ways. One of the ways is absorption. So electrons can absorb photons depending on the energy or depending on the frequency or wavelength of the photon. And if an electron absorbs a photon, it transitions to a higher energy state. It's called a quantum jump, colloquially. That's one thing that can happen. In which case, the light that light quantum is absorbed by the atom, and it doesn't reflect it, right? Another way light can interact with matter is by scattering. So it can be scattered by electrons, which changes the direction of the light, of the photon. And then there is re-emission. So absorbed photons can be re-emitted as light, which can happen at different wavelengths. So these interactions, they prevent light from simply passing through most materials unimpeded. Then you have density of matter and material properties. The transparency of a material depends on its density and the properties, the structure, the atomic and molecular structure of the material. So solids typically have tightly packed atoms, which increases the likelihood of light matter interactions, which increases the likelihood of absorption or scattering or something. Liquids have more, they are less dense than solids, which allows more light transmission. And gases are the least dense of the states of matter, will not go into plasma. So that's why air and many gases appear transparent or translucent. Transparency also depends on the wavelength of the light. Okay, so visible light interacts strongly with many materials, which makes them opaque or reflective. X-rays are a whole different matter, and so on. So all of these effects put together ensure that most matter is not transparent. So yeah, it all boils down to quantum mechanics and the way that light interacts with atoms. Essentially, the way light photons interact with electrons of an atom.